Hi everyone, my name is Oki Gunawan from IBM TJ Watson Research Center, Yorktown Heights, New York. Thank you for taking your time attending the IEEE PVSC virtual meeting 2020. So I would like to present our recent exciting discovery on what we call carrier resolve photo Hall effect, which in essence we unlock a 140-year-old secret in the Hall effect. So first, I would like to acknowledge our collaborator, Professor Byung Hashin from KAIS and David Mitzi from Duke University, also my former IBM manager, and the team member Seung Ryul Pei from KAIS, Doc Bishop, and Yudhisthira from IBM. So I will start with the outline of this talk. First, I will describe the background, the brief history of Hall effect, and then next, the theory of the carrier resolve photo Hall effect. And third, the experimental setup that we use at IBM called parallel dipole line Hall system. And fourth, the experiment and results using this technique. And I will close with summary. So as a big picture motivation of this research is to understand the charge carrier properties in semiconductors or electronics material. So obviously we know the importance of semiconductor technology in our modern civilization. With this material, we built many devices like passive, logic, memory, optoelectronics, and photovoltaics, and recently neuromorphic devices, as well as various kind of analog devices. So the central theme in this research is to understand the full detail of all the charge carrier involved in this material, whether they are majority and minority. So therefore, we could develop the application that we want. So to do this, everyone must know one of the most important effects here, which is the classical Hall effect that allow us to understand the charge carrier properties in the material. This effect was discovered by Edwin Hall in 1879, and his research was motivated by Maxwell's work on electromagnetism that was developed during his time. And from this effect, you could obtain three fundamental information, which are the type, whether it is positive or negative, or hole or electron, and two, how much of this charge carrier are there, or the density, and third, how fast they move, or the mobility mu. So to understand this Hall effect is pretty simple. You just need to recall what you learned from Physics 101, which is the Lorentz force. So when you have a flow of charge along the electric field E, and you have a perpendicular magnetic field B, the charge carrier will get deflected towards one side, and you could measure this deflection as the Hall voltage. So in recent decades, the Hall effect also served as a fundamental basis for advances in physics. Specifically in 1980s, von Klitzing discovered the integer quantum Hall effect, which you could find which you can do in a two-dimensional electron or Hall device. So in this experiment, when you measure the Hall resistance as a function of increasing magnetic field, you observe a quantized step, which is associated with the quantization of the cyclotron orbit of that charge carrier. This quantization is very precise. The quantity is Planck constant h over electron charge square, which is very precise, equal to 25.8 kilo ohm, which is what we know now as the von Klitzing constant RK. And later on, Stormer and Sui from Bell Lab extended von Klitzing experiment to higher magnetic field and even higher mobility and higher quality material, and they observe a new quantum regime where there are quantized steps which are not associated with integer quantization anymore, but rather associated with the fractional states as shown over here. And this regime is essentially a new regime of many-body quantum Hall effect, where the full theory is developed and explained by Bob Laughlin from Stanford, and three of them received the Nobel Prize in Physics for the discovery of fractional quantum Hall effect. So those two serve as an example how important and fundamental are the Hall effect is in the recent decades. So now we're going to talk about the theory of the carrier resolved photo Hall effect. And just as a background, this work was done under IBM photovoltaics program, where we developed a world record copper zinc tin sulfur selenide or CZTS solar cell, where in 2014 we achieved a world record efficiency of 12.6%, where the record still stands until today. And part of this research is the burning question of how we could understand both majority and minority carrier properties in those material, and especially for photovoltaic, you really need to know all the information you could get about minority carrier. So before we go in detail of the photo Hall effect, let's review what we know in the classical Hall effect. Here, in essence, you perform two measurements. One is longitudinal measurement, where you pass current along your device and you measure the longitudinal voltage. And here you can get the resistance and therefore conductivity. And in the transverse or Hall resistance measurement, you measure the voltage perpendicular to the current flow. And from here, you get the Hall resistance Rxy, and you could also calculate Hall coefficient given as with this formula. And finally, you obtain three information, which is the type, whether it's Hall or electron, from the sign of Hall coefficient, the density, which is just inverse of E times H, where E is the electron's charge, and mobility, which is a product of conductivity times Hall coefficient. So what happens when you do the Hall effect with light? So just now what I described is the classical Hall measurement without light or in the dark. So imagine you're only dealing with P-type material. So therefore you're only dealing with Hall in the dark. But under light, you also have a minority carrier, which are electron. And here in this situation, under constant illumination, you could start with assumption that the excess electron is equal to the excess Hall, delta N is equal to delta P. And now your transport problem become more complex because both conductivity and Hall coefficient contain both species of Hall and electron, as shown over here. And beta here is the ratio between the electron and Hall mobility. So until recently, we did not know how to extract both majority and minority carrier information simultaneously in the photo Hall experiment. So the key problem is this: when you measure the conductivity and Hall coefficient in the photo Hall experiment under increasing light intensity, what you observe is that your conductivity increases, but Hall coefficient drops. And sometimes the polarity get inverted because, for example, you could start with the majority Hall, but under high light intensity, the minority electron could have higher mobility and therefore dominate the transport, and you could invert the Hall coefficient. So in essence here, in this two carrier transfer problem, you have three unknowns, which are the Hall mobility mu p, electron mobility mu n, and the photocarrier density delta n at every light intensity, while you only know two quantities, sigma and h, conductivity and Hall coefficient. So therefore, you are lacking one more information. Fortunately, there is a beautiful trick that we discovered that led to the hidden information in the photo Hall effect. So this requires what we call the Duncan or thought experiment in physics, which is essentially a killer trick to solve a very hard physics problem. A famous example is what Einstein did in developing his theory of special relativity. He imagined a thought experiment where he is zipping around on the rocket ship with the speed of light, and he observed a few oddities. Like, for example, if you look into the light wave, he thought that the electric field and magnetic field should be standing still because he's moving at the same speed of light, but that doesn't make sense because Maxwell equation requires the changing of electric field and magnetic field for the the radiation to propagate. So therefore, he concluded that maybe the speed of light is constant, which is indeed to be true. So this is an example of how a thought experiment could lead to a new insight. And this is what we did with the photo hole experiment. This is the Gedanken experiment or thought experiment in the photo hole problem. You imagine two type materials, A and B. They are both are identical, except the second material B has faster minority carrier, or it has faster electron in this example. So, and what happened is that when you perform the photo hole experiment, when you measure conductivity, it increasing light intensity, and Hall coefficient with increasing light intensity, the trick is that you need to plot them as H versus sigma curve. And you perform the photo experiment from the dark to a maximum light intensity and keep plotting the data points. And what you observe is that both material will produce different sigma H curve. In fact, the second material, the material B, because it has a faster minority carrier or a faster electron, the trajectory of H sigma curve is more prominent. And by the way, this curve is derived from the two transport equation that I show in the previous slides. So the clue here is that the trajectory or the slope of this curve contain the information of minority carrier. And therefore, when you do the math, I encourage you to derive this by yourself, and I could assure you can do this in 50 minutes. You start with the two carrier transport equation for both conductivity and Hall coefficient, and try to look for the slope H over sigma and see how does this give you. And what you will find is that the derivative of H over sigma times sigma square plus 2H sigma, or you can simplify this into the derivative as sigma square H over sigma. This gives you the difference in the mobility, or delta mu, or the whole mobility minus electron mobility. So this is a new interesting information that is kind of hidden in the photo hole experiment. And interestingly, there is another form of this equation, delta mu. You could also express it in the logarithmic form as shown over here, which again, you could derive it by yourself. And this is relevant to use when you try to analyze the data in perovskite as shown over here. So in essence, now we have a new equation that give us the difference in mobility between Hall and electron, and there are two expression, equivalent expression for this, which is the low injection version given as on as sigma square H over sigma, and then also the high injection version given as the equation on the top right hand side over here. And furthermore, this new information give you the third information that allows you to solve the three unknowns. First, you have to solve for beta, which is the ratio of electron over hole, which is given as a long equation over here. This is essentially just a solution of quadratic equation. And given the beta, then you can solve for hole mobility, electron mobility, and finally photocarrier density. And you can repeat this at different light intensity. And now the theory, the new theory itself, unfortunately, is not enough. You also need to have the right experimental setup to perform the experiment, which led us to the tool that we use called IBM parallel dipole line hole system. And I want to mention is that it is very important to have AC Hall system to perform this photo Hall measurement, meaning that you have to perform the Hall effect with the oscillating magnetic field so that you can recover a tiny signal that is otherwise very difficult to measure, either because your mobility is too low or your resistance is too high. Just as an illustration, here's an example of the Hall measurement with AC magnetic field in several material, indium tin oxide number one, CIGS, zinc oxysulfide, and CZTS. And the mobility keep decreasing as you go uh, to the bottom. And the quality of Hall signal depends on the ratio between transverse Hall resistance RXY over the longitudinal resistance RXX, which is given as B times mu product. So this is obvious. In order to get a large Hall signal, you need both high enough magnetic field and high enough mobility. And what happens is that when your mobility is very low, and you can see on the right hand side, the whole oscillation becoming more obscure, but fortunately you still can detect it using Fourier analysis shown on the right hand side. So this gives you an idea that in order to recover a very small Hall signal or Hall signal buried under noise, you need to perform AC Hall measurement. So just as a note, there are many groups have developed AC Hall measurement, and this has been developed even 1967. But what we did at IBM is a unique approach using a system called PDL, or parallel dipole line magnetic system, which I will describe shortly in the next slide. So the PDL system is actually it comes from other area of research, which is a research for magnetic trap. So a parallel dipole line system is essentially a magnetic trap system consisting of two magnet with transverse magnetization, meaning that the pole of the magnets are on the curved side rather than on the flat side. And in this kind of system, it produces a confinement effect called camelback potential that could trap a diamagnetic material at the center, as shown over here. And what is interesting is that camelback effect is actually a fundamental feature of electromagnetism, which comes straight from the electrostatic and magnetostatics law. And in essence, if you have two lines of dipole as shown over here, you could expect that the magnetic field is stronger at the center, and then it will decay at both edges. But what is surprising is that if the dipole line, the length of the dipole line is long enough beyond certain critical length, which is given as this, you have a magnetic field which is stronger at the edges compared to the center, and therefore give you the confinement trap. There is a fundamental explanation of how this confinement potential develop. You can partition this dipole line into four linear charges as shown over here. The red one is the interior charges, and the green one are the exterior charges. And you take the superposition of the field that they generate, and you will arrive at this conclusion that the total magnetic field has this kind of camelback shape that give you the trapping behavior. So this system is very interesting because you could develop this into a useful application, such as a magnetic levitation vibration sensor or seismometer, where using this system you could detect an earthquake vibration as shown over here. This is actually a test of our prototype that we did together with our collaborator in Italy recently. Furthermore, there is even a new external article about this camelback potential, which you can find in Wikipedia with the link as shown over here. So now getting back to the photo hall experiment, the PDL system is also very important because for the photo hall application, because this allows us to generate an oscillating magnetic field. And in the photo hall experiment, you also need to have an optical setup to allow the laser to come and illuminate your sample. And also you could perform the reflectivity and absorption measurement in the same setup to get the optical constants for the photo hole analysis that we will do later. So the operation of the PDL system is pretty interesting. When you rotate the master magnet at the bottom, the top magnet or the slave magnet will follow. And what happens is that they generate a counter-rotating magnetic field. So the master magnet at the bottom produce the counterclockwise magnetic field, the red color, while the top or the slave magnet produce the clockwise rotating magnetic field. And as a result, you produce the total magnetic field, which is the blue color, which has four important properties. First, it is unidirectional. It's always pointing vertical, which is what we want for the Hall effect. And second, it is a pure harmonic, meaning that it only contains a single component, which you can express as cosine omega t. And it produces a very strong field up to 1 Tesla. And also you could spin it at any frequency you want. So this is much better compared to using electromagnetic coil to produce XC magnetic field, and therefore we use this in our experiment. And furthermore, there is also some signal processing steps that we need to do. First, as you spin the magnet, you record the whole resistance as a function of time. And on the top, you see the oscillating magnetic field. And then at the center, you see the Hall signal. And then we perform first Fourier transform of that Hall signal to inspect whether you have the Hall signal that you want or not. And second, you extract that amplitude using a lock-in detection to get the final Hall signal that you want. So the baseline of this tool also has been available commercially by our partner Semilab, which you can see over here. But this one has not included the photo hall capability yet. But nevertheless, several groups around the world has used this tool for mainly photovoltaics research. Now I switch to the next section where I describe the results of both the theory and the experiment to perform carriers of photo hall effect. So first of all, we perform this photo hall measurement on a champion perovskite material, and you can see the Hall coefficient and conductivity changes from dark to maximum light intensity, spanning 3 orders of magnitude for conductivity and also about 3.5 orders of magnitude in Hall coefficient. So they change a lot from dark to absolute or maximum brightness. So from the slope of this H versus sigma curve, and given this formula, you could calculate the mobility difference. In fact, the interpretation is also simple. First of all, the slope is always negative. If the slope is close to -2, delta mu will become 0, and you can tell that the Hall and electron mobility are equal in that situation. And therefore, if let's say the slope is less or larger than -2, you could conclude similar situation whether the Hall is larger or less than electron mobility as shown over here. So the new formula allows us a very quick interpretation of the photo hall data that we have. And then given the information of the delta mu, as I mentioned earlier, we could solve for individual Hall and electron mobility as plotted here. And then also the photocarrier density delta n as a function of increasing light intensity. So we also plot a single carrier mobility, it's called mu Hall, and then single carrier Hall density n Hall, which is essentially a number if you assume there's only a single carrier. And this is essentially what people could do in the past before the discovery of this new technique. So as you can observe is that what you observe is that the Hall and electron mobility are about 10 and seems to increase as a little bit as a function of increasing light intensity. And more importantly, we also observe for the first time the excess carrier density delta n as a function of increasing light intensity. And even you can see two different regime of recombination here, which is indicated by the slope m, where m is the power exponent of delta n versus g. And furthermore, given this information, you could extract additional important parameters from your material. Like for example, the given the mobility that you get and also the photon density that you could calculate from laser light intensity calibration, you could calculate recombination lifetime. And given the lifetime and mobility, you could also calculate diffusion length for the three the three kind of diffusion length here for hole, electron, and ambipolar type. Ambipolar type meaning that you have both electron and hole population drifting together, so therefore they are dragging each other, and the correct expression for such kind of ambipolar transport is given over here. So now you could obtain much more information than before, and which is summarized over here. So on the top left panel is your raw photo Hall measurement data. On the top right is your Hall coefficient versus conductivity, and the bottom is the 7 information of Hall electron mobility, photocarrier density, and lifetime and diffusion length as a function of either light intensity or carrier density. So this is exciting because you could finally uncover much more information. So the example just now on perovskite is an example of photo Hall analysis in high injection regime, where the excess carrier density is much larger than the background carrier density. We could also apply this technique to single crystal silicon, which illustrate the analysis in low injection regime, where the excess carrier density under light is smaller than the background, the dark carrier density. So obviously the technique also applies, and you could also obtain the same sets of result. And in fact, the electron and hole mobility that we obtained here is similar to the textbook value, and I invite you to read more details in our publication here in Nature below. In summary, this technique is exciting because it allows us to unlock new sets of 3 layers of information that were not accessible before. So it started with the delta mu equation, and this allows us to unlock the whole electron and carrier density, and finally this allows you to calculate the recombination lifetime and diffusion length for whole electron and ambipolar type. Furthermore, what is exciting, if you compare this new approach of carrier resolved photo Hall techniques, you practically could obtain all the relevant parameters that you want in your charge carrier, which are not possible using other known semiconductor characterization that we have before. So let me close with final summary. This work is very exciting because this brings us a new advance in understanding electronics material, which is essentially part of almost 2 centuries of pursuit in physics. As we know, we rely on using various excitation in nature, like electric field, magnetic field, and light, to probe the charge carrier inside electronics material. So if we start with only electric field, we only get one parameter, which is conductivity or resistivity, which is essentially Ohm's law. And then Hall effect came along in 1879, and we started to get more information, which are type, mobility, and density of the charge carrier. And here, with the new carrier resolved photo Hall technique, we finally have the new understanding, which is the photo Hall equation, delta mu here, and also a new experimental tool to extract much more information from semiconductor for both electron and hole. So we hope this exciting advance could spur and push further development for many emerging advanced electronics material. So thank you for your time and attention.